In this unit, we're going to be talking about functions. Functions show the mathematical relationship between two or more variables, but in this case, we're going to specifically be looking at two variables, a variable on the x-axis and a variable on the y-axis. So it's really important to look at context of a problem and how the particular equation then represents that context. So in this situation, we have an archer climbs a tree near the edge of a cliff, then shoots an arrow high into the air. So kind of picture that in your mind. The arrow goes up, then comes back down, going over the cliff and landing in the valley 30 meters below the top of the cliff. The arrow's height, y, in meters above the top of the cliff, depends on the time x in seconds since the archer released it. The graph shows height as a function of time. So when we say height as a function of time, we say h equals f of t. In other words, if we put t in on the x-axis, time on the x-axis, then height is on the y-axis. So we could say y equals f of x, where x is time and y is height. That would be another way of showing it. So this is time in seconds, this is height in meters above the cliff. So notice when the arrow, or when the y value is negative, that means it is below the top of the cliff. So this is above the cliff and this has gone over the cliff. Okay, so first of all, what does the y-intercept represent? Well, the y-axis represents the height above the top of the cliff. And we said in the context here that the archer climbs a tree and then shoots an arrow high in the air. So this represents the height at which the arrow is when it's first shot. So it's actually 5 meters above the height of the cliff. So this is the starting position of the arrow. Five meters above the height of the cliff. Okay, now what does the x-intercept represent? Well, the x-intercept is on the x-axis, which represents time. So this represents a particular time when something happens. Well, let's think about this. The arrow is going up in the air and coming down. The y-axis represents the height above the cliff. So the x-axis has to represent where the cliff is vertically. Okay, so at this particular time, looks like about maybe 4.2 seconds or so, that represents when the arrow goes over the cliff. So this is the time at which the arrow goes over the cliff. Didn't really leave a lot of room to write that, did I? Approximately when does the arrow hit the ground? Okay, so let's read the context again. It says the arrow goes up, comes back down, going over the cliff, and landing in the valley 30 meters below the top of the cliff. So you see the 30 here, this negative 30? That means 30 meters below the top of the cliff, and this is where it hits the ground in the valley. So when we see where it hits the ground, we can go look up here and see, okay, it looks like it hits the ground at about 5.2 seconds. So about 5.2 seconds after the arrow is shot. So this is just a fairly basic example of looking at a graph and using it to interpret a context that you're given. In this case, a parabola represents the path of an arrow. It's projectile motion. In this unit, we're going to be looking at all kinds of different functions and how they can represent different real-life situations. Okay, so the next one we're going to look at is braking distance problem. The distance your car takes to stop depends on how fast you are going when you apply the brakes. That makes sense. In other words, stopping distance d is a function of speed s. So in function notation, we would say d is equal to f of s. D is a function of s. So that means that d then is going to be our y value and s is our x value. So that means speed is going to go on the x-axis and stopping distance is going to go on the y-axis. Now it says it takes more than twice the distance to stop when you double your speed. So in other words, when you double your speed, it takes more than twice the distance to stop. Sketch a reasonable graph showing stopping distance as a function of speed. What would be a reasonable domain and range for this function? Well, domain's going to be a little easier. Speed, we can think of how fast does a car go. Okay, so domain, we would expect anywhere from 0 miles per hour to maybe, if a car is speeding, maybe 150 miles per hour. That's probably on more of the extreme end, but somewhere in there. So let's say maybe 30, 60, 90, 120, 150, okay? So something like this. And this is in miles per hour, okay? Now it says, so if you're going 30 miles per hour and you slam on the brakes, how long would it take you to stop? I don't know, maybe 10 feet? I don't know. Let's just say 10 feet. I really don't know. That's a little trickier, okay? Now, so let's say if you're going 30 miles an hour, it would take you 10 feet to stop. Now, if you're going 0 miles an hour, it's going to take you 0 feet to stop. Now, it says if you're going 60 miles an hour, it's going to take you more than twice as long to stop as it did when you were going 30 miles an hour. So let's say this is 20, 30, 40, 50, 60. All right, so 10, 20, 30, 40, 50, and so forth. So in other words, if 30 miles an hour takes me 10 feet to stop, 60 miles an hour is going to take me more than 20 feet. I don't know how much more, so let's just kind of do something like this. So when we make this graph, it's curving up like this. It is not linear. So this is not linear. In fact, it is quadratic. It's like half of a parabola there. And I just know that from reading about this particular function. So what's the range? Well, obviously 0, if you're going 0 miles per hour, it's going to be 0 feet to stop. I don't know how long a long skid mark would be. Maybe 100 feet, maybe 150 feet, 200 feet. I don't really know. So let's just, I'll kind of put a question mark. I really don't know how long a car would take to stop if it was going 150 miles an hour. Probably longer than that, so I'm not really sure on that one. Now, when police investigate an automobile accident, they use the length of the skid marks to estimate the speed of the vehicle. So which variable are they using as the independent variable? In other words, the independent variable is the variable you start with, and then what you are trying to compute depends on that. So they are actually using the length of the skid marks, so they're using stopping distance. So we know that speed determines stopping distance, but stopping distance then also can be used to predict speed, which is what the police officer does. So they would measure the skid marks. Okay, so maybe they see that the skid marks are 45 feet long. So they would take these 45 feet long skid marks, they would use the graph, they would go down and they would say, oh, this guy was going like, 65 miles an hour. Now, that would probably be fine if they were on the highway, but if they were on a road where the speed limit was 40 miles an hour, then they would have been speeding. So, use the length of the skid marks to find the speed of the car. Okay. And I kind of just showed you on the graph how that would be done. So these are just a couple examples. They both happen to be quadratic examples, but we are going to be looking at linear functions, quadratic functions, exponential functions, square root functions, logarithmic functions, power functions, all different kinds of functions that can be used to represent real-world situations. We spent a lot of time looking at sinusoidal functions and how they can be used to represent a number of real-world situations. Many other functions do. So in order to know what kind of functions best represent a certain situation, we are going to first study the functions and learn their characteristics. We're going to review some characteristics of functions in general, and then be able to apply some of those functions then to some data and see how we can use them to make predictions.